Hi everyone, this is our fourth tutorial, not first, fourth tutorial for the Introduction to Media course. I hope you have listened to the lecture before you open the tutorial. Okay, let's start with a quick recap on the lecture and then we will solve problem set 3. Now, in lecture 4, you actually discussed again or more thoroughly the vector graphics and the bitmap images. However, you went into details with the vector graphics. You understood that in vector graphics, images are built up using shapes, and these shapes have points and equations. So actually, every pixel in such an image is identified by a certain coordinate, and these values for the coordinates serve in the equation in order for the software or the application to be able to render and re-render the image and redraw the straight lines, the curves, whatever it has, by having the coordinates of such points in the image. Okay, so you went on a thorough recap on the equations of straight line, the y is equal, which is equal to mx plus c, and the y2 minus y1 over x2 minus x1. And after that, you saw a problem with your eyes. Now, as we have said, the lines that are drawn in the vector graphics images are actually consisting of pixels, okay? So whenever you try to draw a straight line that's not going to have real integers or real whole numbers, a problem is going to arise. What is that problem? It's the jagging problem, okay? It happens whenever the value of the coordinates or the values that are taken out of an equation for a straight line are not integers. And for such a reason, we have a technique that's called anti-aliasing. And what is anti-aliasing? It's actually bounding the straight line that you have with a box, a 1 pixel wide box or something like that, and shading the surrounding pixels that are going to intersect with that box with different grades of gray. And by this, you give the illusion to the user that the lines are somehow continuous. You are trying to overcome the idea of having jagging and cut lines all over your straight line. So actually, when you redraw the line and shade the surrounding pixels, this gives you the illusion that you're having a whole straight line, okay? And this is called anti-aliasing. So anti-aliasing is coloring pixels in shades of gray, and gray, of course, for a black line, whose brightness varies according to the extent of their intersection with an idealized 1 pixel wide line, okay? Okay. After that, you visited another concept, which is transformation. And this is a door opening to graphics, by the way. Whenever you come to taking the graphics course, you'll find that you are going to study a lot of transformations. Okay, so in the transformations, we said that you can actually alter any vector object by having some changes applied to the values that represent them. Such transformations can be like translation, scaling, rotation, reflection, shearing. And for the translation, all you have to do is add a certain quantity or a certain number by which the points are going to move. So let's see, if we are having a line, that's our point that was originally at x and y, and you want to move it in this direction. So actually you have to add a quantity to x, let's call it delta x, and a quantity to y, let's call it delta y. And the new point is going to be x plus delta x and y plus delta y. Clear? Hopefully it's clear. Okay. For scaling, if you want to scale something up, most probably you'll have to multiply it by a value that would, for instance, double it or triple it, or even a fraction number like 1.5. And if you want to scale it down, then you will multiply it by half, 1/3, whatever factor you want. So actually the scaling equation depends on the multiplication by a certain factor. And this factor determines whether you are going to scale up or down, okay? For the rotation, we have the equations that came up out of the proof that was discussed in the lecture, and it ended that you have the x after rotation dependent on the angle of rotation and the previous x and y, and the same goes for the y after rotation. Okay, I'm not going to go through details in this part because it was discussed in the lecture a lot. Okay, after you finish that, you discussed resolution. And we have two types of resolution, either device resolution or image resolution. For a device resolution, we said that scanners and printers are measured having resolutions measured in DPI, pixel density, which is dots per inches. And for video frames and monitors, it was the pixel dimensions like 720 by 1080 or stuff like that. Okay. Okay. For the image resolution, we said that we cannot physically have a dimension for pixels unless we solve this equation first. So you have the pixel dimension over the pixel density, this pixel dimension over the pixel density of the monitor of the device, and by that you can actually get what of the pixel density can be for cameras also, by the way, not for just scanners and printers. By doing this, you have the physical dimension of the image itself, and we are going to solve some problems in that to make sure that you understood it quite well. Now with problem set 3. Now, problem 1 states or says, how would a 1 pixel wide bounding box used for anti-aliasing of jagged lines affect the appearance of 1 pixel wide horizontal line in vector graphics? Now, let's imagine what he's saying. He's telling you that in order to solve jagged lines, we have a technique that we discussed before in the lecture, and that is anti-aliasing. And what did we do in anti-aliasing? We actually had a bounding box that surrounds the line in question, and this bounding box determines which pixels surrounding the line are going to be shaded in shades of gray. Okay, so in this question, he's telling you, what if you have this 1 pixel wide box, and you are actually going to apply it on a 1 pixel wide horizontal line? Now, if you have a horizontal line that looks like this, and you actually surround it by a 1 pixel wide bounding box, as you can see, nothing is going to happen. Of course, pardon my drawing in here because I cannot draw straight lines. If the line itself is a 1 pixel wide line, and you drew over it another 1 pixel wide box, then nothing is going to happen, correct? It's not going to affect it because actually it does not have any intersection with any outer pixels, and in that case, this horizontal line is not jagged. So the 1 pixel wide bounding box is not going to have any effect. It's neutral. Okay. So this is what he says here in the solution. No effect as long as a horizontal line is drawn in an image not connected to other shapes. Now, it does not have any connections to other shapes. There are no outer pixels that need to be taken into consideration, and you need to see whether it intersects with any outer, with any other pixel or not. Okay? Okay. Question 1 is easy. Now let's go for question 2, which was in last year's midterm. Consider a straight line drawn in a vector graphics image of size 5 by 5. So you have an image. I'm going to try to draw it as a 5 by 5 as he says exactly. 3, 4, 5. Okay. 1. This will have to be smaller. Okay. Where the straight line, now this image has a straight line. This straight line has end points defined as follows. Now let's assume that our coordinates will go like this. This is our y, and this is our x. Okay. End point 1 is located at column 1. Column states the x, and draw 0. End point 2 is located at column 4 and row 4. So let's draw this. Now, the first endpoint is at column 1, 0, 1, and draw 0. Okay, 0. Because actually in pixels, you start with 0. Okay, so it starts at 0 and 1, and it ends at 4, 3, 4, and 4. It ends here. And this is a straight line. So actually you would have to shade some pixels in between. Now we have a problem, as you can see, that you don't know whether to shade this or that. We will see, okay? He wants you to A, find the equation of the straight line and identify the row number of each of 2 pixels on the line. One with column number 2 and another pixel with column number 3. So first of all, he wants the equation of the straight line. And as we remember exactly, what was the equation of a straight line? It was y2 minus y1 over x2 minus x1 equals to y minus y1 and x minus x1. This is the cursor, okay? Okay. And after that, he wants you to identify 2 points on the line. And how are we going to identify them? By substituting in the equation. The first line that he wants you to identify, he has the column number, but he doesn't know the row number. This will be one of them, by the way. One with column number 2, okay, column number 2, and another with column number 3. So what he wants to do here is he wants to know which pixels are going to intersect or be on the straight line, okay? Which pixels are the straight line is going to pass through while being drawn, okay? So let's solve the first part first. Now, in order to get the equation, we have 2 points, which were 1, 0, and 4, 4. Okay? And the equation is y2 minus y1 over x2 minus x1 equals to y minus y1 over x2 minus x1. Now, let us substitute with the points. So y2 here is 4, minus y1, which was 0, over x2, which is also 4, minus y1 with the x1, which is 1, equals to y minus 0 over x minus 1. So actually, 4y minus, 3y is going to be equal to 4x now. We stopped at having 3y equal to 4x minus 4. Okay? Now, this means that the y on its own is going to be equal to 4 over 3 x minus 1. Now, we have solved, or we have got the equation for the straight line. Now, what he needs us to do is to get the rows corresponding to columns 2 and column 3. So this means that we are going to substitute with the x once with 2 and once with 3. Okay, so we actually have 4 over 3, and we are going to multiply it by 2 minus 1, and it will give us a 1.33. Okay, and since we have no values for rows and columns that are not integers, we have to approximate this to 1. Okay, for the second part, we are going to actually substitute the x with 3, and this is going to give us a 2.66. Now this can be either 3 by approximation or 2. However, in both cases, you are going to have an incontinuous line. Yani either this is not going to be there, this point is not going to be there, or that point. Now, if you solve this for 2.66 and you approximate, you got the floor for it, and most probably you'll get the floor, so it's going to be a 2. If by any chance you solved it and got the 3, it's going to be a 3. However, in both cases, you are going to have a gap. And for me, I solved it for the floor, so actually we have a 2. Okay. Now we are going to fill in these points. We will find that the straight line is having a pixel missing on that row, this row number 3. Okay. In part B, he wants you to show him how you fill the gaps between the pixels of the straight line. Now we can say that out of this equation, we found out that the line is going to intersect with row number 2 and number 3, because actually we had a part that is a decimal, 0.66, correct? So when we come to fill in the gap, we are going to fill in this pixel with a shade of gray. Okay. The third part, he's telling you, if anti-aliasing is to be applied to the image you obtained in double I to eliminate the effect of the jagged straight lines, show approximately on the figure how you are going to represent the image. Now, the original pixels filled are these. Okay, this is 0, 1, 2, 3, 4, 0, 1, 2, 3, and 4. These are the original pixels on the straight line, the ones in black. All of the other gray are the ones that you are going to shade because the line intersects with parts of them, okay? So you are going to shade these pixels with different shades of gray according to the part by which the line intersects with them. For this pixel, it intersects on a very low level, so we are going to give it a very light shade of gray. For this pixel, it's quite having a larger intersection area, so you are going to shade it in a rather darker shade of gray. and this is going to have the darkest shade of gray because it's actually having an intersection, okay? A bigger intersection. Now, for problem 3, for the image of a circle shown below, approximately sketch on the same figure the output of anti-aliasing. Now, let me erase this because I was actually, guys, recording, and I've done a lot of recording. However, at the end, I found out that I was not recording anything, and it all went down the drain. Okay, does not want to erase. Give me a moment here. Okay, sorry about that. Now, he is telling you that for this image, he wants you to apply anti-aliasing to the output to show an approximation of a circle drawn. So, as we all understand, what is anti-aliasing? It means coloring pixels in shades of gray whose brightness varies according to the extent of their intersection with an idealized 1 pixel wide line to solve the problem of jagged lines that result from undersampling. Now, what we are going to do here is to actually draw a bounding box, okay? This bounding box is going to determine which pixels are we going to shade, okay? And then we are going to loop with this bounding box, and we will find that everything that we are intersecting with has to be shaded, okay? So this bounding box is telling us which pixels do we have to shade. Pardon my drawing, guys. Pardon it. Okay. So all of the surrounding pixels to that circle that are lying within the bounding box are going to have shades of gray like this. Okay, can you see? It intersected all of these pixels. Those pixels, the corners are the most having intersections. So all of these are going to be colored in shades of gray. Okay, now let me erase this also. Hold on a sec. Back to our slide. Okay, if X is a point with real coordinates 120 to 150, what are the coordinates of the point Y if XY is 3 different examples, A, B, and C? Let's draw the givens. Now he is telling us that we are having X with real coordinates. Okay, 120 and 250. So actually 120 and 250 might be somewhere here. This is our X. He wants us to know where would the point Y lie on the grid if a line drawn between X and Y is going to A, run horizontally to the right, having a length of 250. So this means that our Y is going to be having the same value for Y, 250. However, we are going to add to the X the length of the line, exactly. The X is going to shift from this point to that point. So we have to add the length of the line in order to get the coordinates for y, which is going to be 370 and 250. Okay, this is for part A. Okay, for part B, we have a vertical line running upwards. So actually we are going to draw a line upwards from X, and it's having a length of 120. Okay, so in this case, which axis is going to have a different value for the point Y? Exactly, the Y axis. So the 120 is going to be left as is with no changes. However, we are going to add the length of the line to the value of Y. So it's going to be 120 plus 250, and this is the new value for the point Y. Okay? Now, let's solve this if the coordinates were in the image orientation coordinates, X pointing to the right and Y, however, is pointing downwards. So in this case, we will have our point X in here, and he told us that the point Y lies to the right. So we are just going to draw the same line, the Y having a length, XY having a length of 250. So actually, this is not going to change. It's going to be the same. The change will happen in X, and we will just add the 250 to the original value of X. Now, what about B? He told you a vertical line running upwards. So in this case, the 120 is going to what? Be subtracted out of the original length, the original, coordinate of Y, which is 250. So it's going to have 250 minus 120. This is going to give us a 130. Okay. Now, C is telling you that you have a diagonal line running downwards and to the right at an angle of 45. So running downwards and to the right at an angle of 45. So if this is 45, then this has to be 45. And the length of it is 400 units. Now, what would be the coordinates for the Y? Now, for the third part, he's saying that you have a diagonal line running down and to the right at an angle of 45. How would, this is the last part. Okay. So, we now know that there is a line drawn from the point X, and it is having a length of 400. Okay. And it's having an inclination of 45 degrees. So actually, there is some sort of a triangle that can be drawn over here. We know that this is a 45 degree in it. Okay. So actually, we can apply some rule that was in the trigonometry, and I hope that you remember it. It says that sine theta equals to the opposite line over the hypotenuse. Okay, and cosine theta is equal to the adjacent over the hypotenuse. So now we know that our theta is of 45 degrees. Okay, the line opposite to it is going to be our x-intercept. Okay, and the hypotenuse is 400. So we have 2 unknowns out of 3, so we can get the third. Now, since the hypotenuse is 400 and the sine theta is sine 45, therefore it's root 2 over 2 multiplied by 400. So it's going to give us like 282 something, point something, okay? And the same goes for the adjacent line. It's going to be cosine theta multiplied the hypotenuse, root 2 over 2 multiplied 400. So it's going to give us the same value. Now, what we have said are the lengths of the line, not the coordinates. So how can we know the coordinates? We are going to add 120 to the length of the line, which is 282. And for this part, we are going to get 282 minus 250, because actually the point is down at the negative y part, okay? So again, the final coordinates are going to be 250 plus the 282 plus the 120 originally of the x. And for the y, it's going to be 282 minus the 250, which is going to give us a negative 32. And for the x, is going to give us a 402. Now, the last question that he wants you to answer for this problem is how would your answers be different if x and y were pixels? Now, if x and y were pixels, guys, what should we know about pixels? Well, pixels have only non-negative integer numbers. So all of the decimals are not going to work, and all of the negatives are not going to work. So we are not going to accept the point y. We will have to do some alternation to it in order to be able to accept it. Okay? Okay, in problem 5, you are given an 8-bit grayscale image, which appears to be 4 inches wide and 6 inches high on your 72 dpi monitor. He wants you to calculate the number of pixels in the image, to know the raw file size for this image and convert it to kilobits, to determine how big will it be if you print it out on a 1000 dpi printer, and to determine how many shades of gray can be displayed in this image. Okay? Now, what are we going to do for the first part of the question? Okay. We know that the image is physically 4 inches and 6 inches high on a 72 dpi monitor. In order to determine the number of pixels, we will need to multiply the 4 inches by the 72. And why is that? Because the unit is telling you that the monitor is having 72 dots per inch, okay? And since the width is already 4 inches, this means that the number of pixels on the width is 4 by 72. And since the height is 6 inches, so it means that the number of pixels on the height is 6 by 72. Okay? So the pixels are actually the points, the dots. And the total number of pixels in the image is going to be determined by 4 by 72 by 6 by 72. Okay, so we actually get the result of the width, the result of the height, and we multiply both by each other to get the total number of pixels in the image. Okay? Okay. This is for the first part. In the second part, he wants you to calculate the raw file size for this image and convert it to kilobits. Now, the raw file size is determined by the number of bits in the grayscaled image without any compression. So we will get the number of pixels in the image and multiply it by the number of bits. Okay? The number of pixels in the image and multiply it by the number of bits representing every pixel, and this will give us the file size in bits. In order to convert it into kilobits, we will just have to divide it by 1000. Okay? Now, the third part of the question is, how big will it be if you print it out on a 1000 dpi printer? We know how many pixels we have in the width and how many pixels we have in the height. And we want to determine how are we going to represent these pixels on a printer or using a printer that is having a 1000 dots per inch. So how are we going to do this? We are going to divide the number of pixels on the new resolution to get the physical dimension by which it's going to be printed. So the number of pixels for the width is 288, and the new resolution of the printer is 1000. So it's going to occupy an 0.288 inches when printed. The same goes for the height, the total number of pixels divided by the resolution of the printer. So it's going to give us an 0.432 inches, which is the height by which it's going to be printed. The final part, or the last part of the question, is telling you how many shades of gray can be displayed in this image. This is pretty easy. You know that this grayscale image is represented, every pixel is represented in it using 8 bits. So this means that the total shades of gray that you can have in this image is 2 to the power 8. Your color palette should contain 2 to the power 8 gray shades of gray, which is 256. Okay, problem 6. An image appears to be 3 inches by A inches on a 150 dpi screen and B inches by 2 inches on a 100 dpi screen. Each pixel is represented using 24 bits. He wants you to first find A and B, and finally find the size of the image file in kilobits. Now this is an easy question regardless of the unknowns. It's very easy. Now if you have an image to be 3 by 8 inches on a certain screen and having other dimensions on another screen with different resolution, actually the two images have to be somehow proportional. So the widths are going to be equal and the heights are going to be equal. So in this case, the 3 multiplied by the 150 is going to be equal to the B multiplied by the 100. The dimensions, guys, has to be proportional, okay? Because it's actually representing the same image. So in here, the B is going to be equal to 450 over 100. So it's going to be equal to 4.5. For the A, it's the same, A by 150. Is going to be equal to 2 by 100, which is 200. So actually the A is going to be equal to 1.33. Okay? Now the second part, he wants you to calculate the size of the image file in kilobits. And how do we get the size? Perfect. By multiplying the number of pixels you have with the number of bits you have. Now the number of pixels is determined by what? The number of inches multiplied by the screen resolution. So we can take either dimensions. We can take the 3 and the A and the 150, or the B and the 2 and the 100, and both will be correct. So actually we can multiply the 3 by 150 by the A by the 150 by 24, or B by 100 by 2 by 100 by 24, and both of them will give us the correct size. In bits, he wants it in kilobits, so you'll have to divide by 1000. Okay? Okay, this is the final question for problem set problem set 3. However, there was a certain problem with problem set 1 that I need to make sure that all of you understood. It was something wrong that went with the first recording, and I want to make sure that all of you understood it from the tutorial. If you remember solving this question, we did quantization and sampling. However, there was a certain error here. When we solved it in the first recording of tutorial 1, I have posted the correct solution, and I just wanted to make sure that you understood that in the approximation, in this part, you just do approximation. If the point is in between two levels, you just have to approximate it. If it's less than 4.5, then it's going to go to the lower level. If it's higher than the whatever 0.5, it's going to go to the upper level, and that's it. Just mere approximation, nothing more. Okay, just needed to make sure that all of you understood this. Okay, hope you understood, guys, and see you in the next tutorial. Bye.